Oh, welcome to this lecture on pharmacokinetics. And I want to just preface this lecture by letting you know this is really just a brief overview, an introduction to a really large field of study. And pharmacokinetics, as we'll define here in a little bit, covers all sorts of different things. And if you just look at this outline, we're going to essentially cover some of the topics that have some mathematical calculations that can be performed to kind of show you some of the math skills that will be required in this much more in-depth field of study. You'll have, in pharmacy school, at least 2 whole courses on pharmacokinetics. There's usually pharmacokinetics and then clinical pharmacokinetics. So it is a very broad and in-depth area of study. And we're just going to scratch the surface, introduce you to some of the interesting terminology, and have you practice on some of the types of calculations that you're going to see in much more depth when you actually take those courses. So with that as a real brief overview, let's start by looking at and defining some of the terms so that you understand the terms as we go through these examples. And the first is the term pharmacokinetics. Now that term, pharmacokinetics, is actually a branch of pharmacology that's dedicated to determining the fate of drugs once they're administered to a living organism. By that, I mean pharmacokinetics describes what the body does to the drug, in that it refers to the movement of the drug first into, then throughout, and then finally coming back out of the body. Pharmacokinetics measures the time course of a drug's liberation from its dosage form, then its absorption, distribution, metabolism, and elimination. And each of those sections, all of those sections together, are often abbreviated LADME. L for liberation, A absorption, D distribution, M metabolism, and E excretion. So it really reviews the entire time course of what the body does to a drug once a drug is administered. So let's just use an example. Let's just say you need an ibuprofen tablet to treat a headache from listening to this lecture already. So what you would do is pick up a conveniently formulated dosage form, that is a tablet. Instead of having to disperse and swallow loose powder, we have pre-formulated all of that powder into a convenient solid dosage form that you can just pick up, put into your mouth, and swallow. That's fantastic. That's so much easier to administer. Now, once that tablet finally gets down into my stomach, though, it's got to dissolve. It's got to disperse. It has to release or liberate the ibuprofen from that tablet dosage form. Once it dissolves and disperses and releases the ibuprofen, then that ibuprofen solid powder has to dissolve in the biologic fluid. It has to have the acid in the fluids in the stomach kind of disperse and dissolve the drug. Once it's dissolved, then the ibuprofen actually has to be absorbed across the GI lining. It has to get through the stomach tissue and into the bloodstream. Because again, I'm not taking the ibuprofen to treat my stomach. I want the ibuprofen to get from my stomach and up to my head to treat my headache. So once it gets absorbed through the stomach and into the blood, then the blood has to distribute it. The blood will take my ibuprofen throughout my entire body into a couple of important places. First of all, my head, where my headache is, so it can produce its therapeutic effect. But in this distribution, it also ends up in places like the liver. And the liver has the very important job often of metabolizing or helping to change the drug so that drug is then ready to be able to be eliminated. And this elimination often occurs either back through the GI tract or through the kidneys, through renal elimination into the urine. Okay? And so pharmacokinetics basically characterizes all of these processes using mathematical and statistical models, i.e. that's why it is related to a calculations course. And we're going to just scratch the surface and look at some of those mathematical models or some of the calculations involved in actually modeling how the body is handling each of these sections: the liberation, the absorption, the distribution, the metabolism, and elimination. Okay, so that's why we started with the definition of pharmacokinetics. That's everything that the body does to the drug. Now, we're going to go through some more specific examples, especially focusing here early on with the drug administration part to it. Let's talk about a subsection of pharmacokinetics called biopharmaceutics. Now, biopharmaceutics is a more narrowly focused part of pharmacokinetics in that it examines the interrelationship of 3 things. That is the physical or chemical properties of the drug, as it relates to the dosage form that drug is formulated in for the purpose of administration, and lastly, the actual route of administration itself. And essentially, biopharmaceutics shows how all of these factors affect our drug's onset, duration, and intensity of action. That is, biopharmaceutics can help explain how long it takes for the drug to actually start to produce its effect, how long that drug might be available to produce an effect, and lastly, the amount of drug that actually gets there to be able to produce an intensity or the strength of action that we want. Okay, so it's a very important part that focuses on essentially the liberation and administration, if you will, section of pharmacokinetics. Now, an important term that we're also going to start off with here in a minute is bioavailability, and it's definitely one of the things that is incorporated into biopharmaceutics. Now, the term bioavailability itself is defined as the extent to which an active ingredient or drug moiety is absorbed from the drug dosage form and thereby becomes available at the site of action. Bioavailability can be expressed numerically as the proportion or percent of the administered drug dose that actually reaches systemic circulation. So, for example, an intravenous drug that goes directly into the systemic circulation is 100% bioavailability or bioavailable. It's all there because we put it directly into the blood. That's not the case for other routes. For other routes, for a drug to be absorbed through biologic membranes, it must be first released or liberated from its dosage form and then dissolved in body fluids. Therefore, the bioavailability of other dosage forms other than IV dosage forms can be decreased by a couple of factors such as incomplete dissolution, incomplete absorption through the GI tract, or even first-pass metabolism by the liver, which can eliminate it before it actually gets to the rest of the body. Okay, so we're going to go further in some of the specific calculations here in a minute, but I wanted this slide to kind of overview, and hopefully you have kind of a good understanding now of what the whole area of study of pharmacokinetics involves, and then more specifically that of biopharmaceutics as it relates to things like absorption and liberation of our drug and impacting things like a drug's bioavailability. Let's continue to develop more detail about the idea of this bioavailability. And again, bioavailability is a subcategory of absorption, as it is the fraction of an administered dose of an unchanged drug that reaches the systemic circulation and is one of the principal pharmacokinetic properties of a drug. Now, the term bioavailability factor is abbreviated with a capital letter F. So let's go ahead and define what an F value means. Okay, an F value is calculated by taking the dose of drug that actually reaches the blood and dividing it by the dose of the drug that was actually administered. Okay, it is the fraction. It's a fraction of how much reaches the blood versus how much was actually given. Now, this formula is actually often rearranged such that we can say that the dose of a drug that reaches the blood is actually equal to the F value times the dose of the drug administered. Okay, so for example, when a medication is administered intravenously, its bioavailability is 100%, and thus its bioavailability factor, or F value, is 1. However, when a medication is administered via other routes, such as orally, though its bioavailability generally decreases due to factors such as incomplete absorption or even first-pass metabolism through the liver, and actually can even vary from patient to patient. As such, in these cases, the F value would be less than 1. Therefore, bioavailability must be considered when calculating dosages for non-intravenous routes of administration. So with all of that, let's look at an example to kind of understand this idea. So in this example, we're going to administer 40 milligrams of a drug. And we're going to do that by an IV route, an oral route, and by an intramuscular injection route. And again, an IM injection, while it's still an injection, it's not an injection into the blood, it's an injection into the muscle. So there's still some degree of absorption that's required. Okay, so, and I've given you, for this drug that we're going to administer 40 milligrams, I've given you the F values then for each of those routes. So the FIV value is 1, the F for the oral route is 0.5, and the F value for an intramuscular injection is 0.9. So looking down below at this slide, let's do one thing at a time. And then we'll start with the obvious one when let's start with the intravenous route. The FIV is 1 because we're putting the drug directly into the blood. So it should make sense though, but let's use our formula here and say that the dose of the drug that reaches the blood, therefore, would be our F value, in this case 1, times the dose administered, which is 40 milligrams. So 1 times 40 milligrams equals 40 milligrams. So it should make sense for an IV administration that if you inject 40 milligrams IV, you get 40 milligrams into the blood because that's where you injected it. Now, let's go into more complicated examples. Oral. Let's say we take the same drug, formulated it as a tablet, and swallow the tablet. Okay, how much of that drug is actually going to reach my blood? Well, we were given that the F value, or the bioavailability factor for this drug for the oral route, was 0.5. So if I use my formula, I can say that the dose of the drug that reaches the blood would be equal to that F value, 0.5, times the dose administered, which was 40 milligrams. 0.5 times 40 equals 20 milligrams. So of the 40 milligrams I ingested, only 20 milligrams reaches my blood because the bioavailability factor is 0.5. And what makes it 0.5? We don't know. But maybe the tablet doesn't completely dissociate. Maybe the drug is not particularly water soluble. Or maybe it's a rather polar molecule and therefore doesn't get absorbed across tissues very well. Whatever the reasons I should say, when we administer it orally, it turns out we lose 50%, meaning we have a F factor of 0.5 for an oral administration of this drug. And our last example is intramuscular, or IM. And there are many drugs administered by injection, but not IV. Again, intramuscular means into the muscle. And so antibiotics or vaccines, other medications are administered via an intramuscular injection. In this case, we're saying it's much better than the oral route, but it's still only about 90% absorbed. That is, the F value for the intramuscular injection is 0.9. Thus, we can calculate if we injected 40 milligrams of our drug, then the dose of the drug that reaches the blood would be the 0.9 times the 40 milligrams. And therefore, we'd have a total absorbed dose of 36 milligrams. All right. So hopefully that makes sense. It's not a difficult concept. The bioavailability factor, or F value, represents a fraction. It is the fraction of the amount that actually reaches the blood as it relates to the amount that was absorbed. Okay. Now, let's go a little bit further with this F value and use it in a more applicable sense. And that is, we have to define bioequivalence. Okay? So another reason to use this bioavailability factor, or F value, is to determine bioequivalence. Bioequivalence is the term in pharmacokinetics used to assess the expected biological equivalence of two different preparations of the same drug. If the two products are said to be bioequivalent, it means that they would be expected to produce the same degree of effect in the same time course of both onset and duration. So, in this example, let's compare the bioequivalent doses to 40 milligrams IV. Because I know when I give 40 milligrams IV, I get 40 milligrams into the blood because I'm going directly there. That's not necessarily the case when I do both oral or intramuscular. The question here, though, is, well, if I need 40 milligrams of my drug to be in the blood, what is a bioequivalent oral dose and what is a bioequivalent intramuscular dose? Bioequivalent meaning they would provide the same dose in the blood as my 40 milligrams IV. So let's determine bioequivalent doses. All right. We'll use the same formula that we did before. That is that the dose in the blood is equal to the F factor times the dose administered. But in these questions, we're reversing what we know. What we know now is the dose in the blood that we want. We want the dose in the blood to be 40 milligrams. So the question is, how much dose do I actually have to administer? All right, so let's start with the first example with our oral dosage form. And we know that the bioavailability factor, or F value, for our oral form is 0.5. So we're going to set up the equation as 40 milligrams, which I'll remind you represents the dose in the blood, the dose we want to obtain in the blood, that is 40 milligrams, is equal to the F factor, which in this case we said was 0.5, times X. And in this case, X represents the dose to administer of the oral form. So if we solve for X by simply taking 40 milligrams and dividing by the 0.5, we would determine that X equals 80 milligrams. What that says is I have to administer 80 milligrams orally to obtain a 40 milligram dose in the blood. And that's because my oral form has a bioavailability factor of 0.5. That is, only 50% of what I give orally is absorbed into the blood. Therefore, I have to give 80 milligrams orally to get 40 milligrams into the blood. All right, let's do the same sort of thing for the intramuscular. Once again, I want 40 milligrams of my drug into the blood, but my bioavailability factor for an intramuscular injection is only 0.9. So I could set the amount that I want in the blood, 40 milligrams, equal to the bioavailability factor of 0.9 times X. And again, X is the dose that I need to administer via an IM injection to get 40 milligrams in the blood. Solving for X, I would take 40 divided by 0.9 and see that X would equal 44.4 milligrams. Meaning, if I administer 44.4 milligrams via an intramuscular injection, then I would eventually get 40 milligrams of my drug absorbed into the blood. All right? And so to summarize all this, now to come back to the term bioequivalent, what we can say is that a 40 milligram bioequivalent dose would be 40 milligrams IV would be the same as 80 milligrams oral and 44.4 milligrams IM. All four of those doses, 40 milligrams IV, 80 milligrams oral, and 44.4 milligrams IM, would all produce the same degree of effect and the same way, and they are bioequivalent. So that is a way that you can use this availability factor, F factor, to be able to determine a different bioequivalent doses for different routes of drug administration. All right, let's practice some more of these bioequivalence type questions. And our first question to practice with says, how many milliliters of a methotrexate injection containing 50 milligrams per 2 ml would be considered bioequivalent to a 15 milligram tablet? And note that I provide you that the bioavailability factor for methotrexate oral is 0.4, and the value for the subcutaneous injection bioavailability factor is 0.8. All right, so we want to know how many milliliters of the injection would be equivalent to one of these 15 milligram tablets, given the fact that the bioavailability is different between the oral and the subcutaneous. So where do we start? Well, let's use our formula. We know that the bioavailability of any product is its bioavailability factor, F value, times the dose. And bioequivalence would say that that amount, that is the F value times its dose, the bioavailability, would be equal in two products that are bioequivalent. So we can say that the F value of the first dosage form times its dose, F1 times dose 1, is equal to, if they are bioequivalent, then the F2 dose 2 for the different dosage form. So the F times the dose of the first dosage form would be equal to the F times the dose of the second dosage form if the two products are bioequivalent. In this example, what we want is the dose of the injectable that gives us a bioequivalent dose to the oral route. Okay, so we're going to set up F1 and dose 1 equal to the values for the tablet and set F2 dose 2 equal to the values for the injectable. So let's go ahead and set that up. For the oral side, we were given that the oral bioavailability unit, or F unit value, would be 0.4. And we're going to multiply that by the dose of the tablet we were given at 15 milligrams. That is what we want to be equal to, that is the same as bioequivalent to our injectable, which we know has an F value of 0.8 when given subcutaneously, times its dose. But we don't know the dose, so we're going to set X equal to the dose of the methotrexate injection that is bioequivalent to the 15 milligram tablet. So now we need only solve for X. So 0.4 times 15 is equal to 6. And that would equal 0.8x on the right side. So now if we solve for x by dividing both sides by 0.8, we see that 7.5 milligrams is the dose of the subcutaneous injection that would be bioequivalent to one 15 milligram tablet. So now to answer this question, what we need to do is calculate the milliliters, or the volume of the injectable that we have to provide the 7.5 milligrams. So to do that, we'll take our target dose of 7.5 milligrams and multiply it times the concentration, expressed as for every 2 milliliters, there it contains 50 milligrams. So milligrams cancel, and when I multiply 7.5 times 2 divided by 50, my numeric answer would be 0.3, and the value would be milliliters. So I know that 0.3 milliliters of a 50 milligrams per 2 ml in concentration injectable of methotrexate, that volume 0.3 mils, if injected subcutaneously, would provide the same bioequivalent dose as if we had swallowed or taken orally a 15 milligram tablet. Let's perform one more bioequivalence calculation or question. And this time, in the previous question, we did a tablet versus an injectable. Now let's do a capsule and compare it to a topical cream or an ointment in this case. Okay? So this problem reads, a drug, and in this case, we're going to use nitroglycerin as our example. So nitroglycerin, this drug, is 40% bioavailable by the oral route, and 58% bioavailable by the transdermal route, that is, meaning when applied to the skin. If a patient is taking 2.5 milligram oral dose twice a day and is switched to a 2% weight per weight ointment, how many grams of the ointment should be administered as a single dose to provide a bioequivalent dose of the drug? Okay, so what we're wanting to do is take our oral dose that we're getting and find a bioequivalent topical or ointment-based dose. So first step in this question, though, is determine the total daily dose that we are getting of our nitroglycerin from the oral route, because we were told we were taking 2.5 milligram capsules, but doing those twice a day. So we need to start with the fact that, okay, if I have 2.5 milligrams per dose, times the fact that I'm doing 2 doses per day, then doses cancel, and we can see that what we're trying to replace is 5 milligrams per day of the nitroglycerin. That's the bioequivalent dose I need, the dose that provides me 5 milligrams per day. So going back to the definition of bioequivalence, that occurs when your bioavailability factor times the dose you give is equal to the bioavailability times the dose you give from a different dosage form. If those are the same, then the 2 different dosage forms are considered bioequivalent. Okay, and that's what we want in this case. So let's set this up by setting our oral values on the left. So we were given that the bioavailability factor for the oral route for nitroglycerin is 40%. That essentially is the same as a fraction of 0.4. 40 divided by 100 is 0.4. So the F value for the oral is 0.4, and we're going to multiply it by the total daily dose, which we just calculated to be 5 milligrams. Set that equal to the F value when we apply nitroglycerin topically, which we were given as 58% bioavailable. So we would divide 58 by 100 to get a fraction of 0.58. So the F value for the topical is 0.58. times the dose. And the dose is what we're solving for. Essentially, we're going to set that equal to X. X equals the dose of the ointment when applied topically that provides a bioequivalent dose as taking 5 milligrams of nitroglycerin orally. So now, solving for X, if we multiply 0.4 times 5, that would equal 2 on the left, and set that equal to 0.58 times X. Divide both sides by 0.58, and we see that X equals 3.44 milligrams. The dose of the nitroglycerin I need on a daily amount to replace my 5 milligrams per day of capsules would be an amount of ointment that provides 3.44 milligrams of nitroglycerin. So I have my target. To answer this question, though, I have to determine the actual grams of ointment that I'm using to provide the 3.44 milligrams. So to do that, let's start with my 3.44 milligrams, and let's convert that to grams by multiplying by the fact that for every 1 gram, there would be 1,000 milligrams, so the units of milligrams cancel and I'm in grams. Then I can multiply that by the concentration of my ointment. I was told it was a 2% weight per weight. So I'm going to multiply that by the fact that that means for every 100 grams of ointment on top, there would be 2 grams of nitroglycerin. So grams of nitroglycerin cancel, and I would be in grams of ointment. So if I do that math left to right, my final value would be 0.17 grams of this 2% weight per weight nitroglycerin ointment. That weight of ointment actually provides me 3.44 milligrams. That's the amount of nitroglycerin that is bioequivalent to actually taking 2.5 milligram capsules, or essentially 5 milligrams of capsules orally. So that's how these bioequivalence calculations can be very useful when you need to go from one dosage form to a different dosage form and need to get the same amount of active ingredient in the 2 different dosage forms. And that goes back to the whole idea of bioequivalence and this kind of works at the whole concept of the absorption phase or the absorption part to pharmacokinetics. Our next topic is a very important one to understand the remainder of this lecture, which is what happens to the drug once it is absorbed. So we've gone past bioequivalence and bioavailability. We're now assuming what happens once the drug starts to be absorbed. And this example on this slide is from an oral medication. So we've swallowed a pill or a tablet or a capsule, and it's now being absorbed. How can we describe and visualize the processes that occur once that happens? Well, a plasma drug concentration time curve does a really good job, and especially if you understand how to interpret it. I know looking at the slide, there's a lot of information on here. Let's start with this. Let's look at the graph and know what we're graphing. On the x-axis is time. So going from the far left, which is time 0, to as you progress to the right, we have increases in time. Okay, now the time is not specific on this graph, but as going from left to right, time is increasing. Then on the y-axis, we're looking at the plasma drug concentration. So again, at the very bottom, at time 0, 0, again, on the y-axis, we would have 0 plasma concentration. There would be no drug in the plasma before it starts to be absorbed. But as it starts to become absorbed, the plasma concentration increases. Okay, so time on the x-axis, plasma concentration on the y-axis. So before we look at all the specifics here, let's just look at the dark line. So starting at time 0, 0, the dark line, you'll notice, rises rapidly as we progress through time and then tends to peak. And where it tends to peak, so this kind of rapid increase curve till it peaks at T max. So T max stands for the time of the maximum plasma concentration. So on the x-axis, going from time 0 to T max is the time it took to have complete absorption. Because you'll notice T max, if you go from the time up to the curve and then to the left on the y-axis, T max produces the Cmax, and Cmax stands for the maximum plasma concentration. Should make sense that Tmax is just the time it takes to get a maximum plasma concentration. What's important about this time, Cmax, is the time where the absorption rate is equal to the elimination rate. So at that point, and you'll notice it tends to slow down a little bit near the top because most of the drug has been absorbed. So at the Tmax, at the time at which the absorption rate equals the elimination rate, there's no more increase in the plasma concentration because the amount of drug coming in is now equal to the amount of drug being eliminated or removed from the plasma. And I'll remind you that can occur through either the liver metabolizing and breaking down the drug and or the kidneys that can remove the drugs through the urine. So regardless of how the drug is being eliminated, at Tmax, the absorption rate is equal to the elimination rate. Now, at times past Tmax, you'll notice that the elimination rate is greater than the absorption rate, to where there may not even be any absorption at that point, and that's why the curve is slowly going down. So the curve then kind of goes down over time due to the elimination phase, and you'll notice at the far end of the right, it's almost completely gone. Okay, the levels of plasma concentration has gone nearly back to 0. So when you swallow a drug, there is a period of absorption, and at some point then, at some Tmax, which is unique for every drug, that absorption now is no longer greater than the body's ability to remove the drug, and from there on out, time-wise, the body is just starting to remove the drug. So that's why the plasma concentrations of the drug goes down to where it's nearly all eliminated. All right, now let's put some interesting other facts. So we've talked about Tmax and Cmax. What is interesting, when you swallow a drug, when does it start to work? How long before it starts to work? That's an interesting question, and it's different for every drug. On this graph, what's important to know is that you'll notice there's a dashed line called MEC, and that stands for the minimum effective concentration. So for a drug to produce its biologic effects, its pharmacologic effects, there has to be enough drug in the system. So you'll notice, even though we start at 0, when we start to absorb, at some point, time-wise, there's an arrow that says onset time. And that's the time unique for that drug where the absorption has produced enough absorption that the concentration is equal to the minimum effective concentration. So at any concentration above the minimum effective concentration, you'll be producing your pharmacologic effect. So the onset time is the time it takes for the drug to be absorbed up to the level of its unique minimum effective concentration. How long does a drug work? Well, the length of the duration of action for a drug is from the time of its onset until essentially the time of termination of its action, that is, until its plasma concentration falls back down below the minimum effective concentration. So the duration of action is the time between the onset of action of its increasing above the effective concentration till the time it falls back down below the minimum effective concentration. So that's the duration of action. The intensity of action is equal, that is, how intense the drug is, has to do with how high its plasma concentration rises above the minimum effective concentration. The higher the peak concentration above the minimum effective, we call it the higher the intensity of action. The only concern with this high intensity of action is we don't want our Cmax, our peak plasma concentration, to exceed what's called an MTC, or a minimum toxic concentration. Remember, we want our plasma concentration to be above the minimum effective, but below the minimum toxic, because if the values go above the toxic level, then we get side effects, then we get toxicity due to our drug, and we certainly don't want that. So the difference in between the minimum effective concentration and the minimum toxic concentration is called the therapeutic range. So we would like our drug's peak plasma concentration to occur somewhere within the middle of that therapeutic range. Well below the minimum toxic, but well above the minimum effective. And that way that can give us a nice long duration of action while the peak concentrations, or while the drug concentrations, are above the minimum effective concentration. So, anyways, the key terms here, well, last thing before we sum up the key terms, is this AUC. In pharmacokinetics, a very important term is the area under the curve, or AUC. And you can see that illustrated in this figure where you see the gray. So it really encompasses the whole area underneath the plasma drug concentration time curve. The greater the AUC, that is, the larger that shape of that curve, whether it's due to a higher peak or a slower elimination, whatever it is that kind of produces a larger AUC, then the body has a larger exposure to that drug. Versus a drug with a very small AUC, meaning that it wasn't very highly absorbed or it was eliminated very rapidly, and therefore the body's exposure to the drug is much more limited. So an AUC is a good way to describe the amount of exposure the body had to that drug, whether, and that includes the couple of things we've talked about. In this figure, we've talked about its absorption, that is from time 0 up to Tmax is absorption. Its elimination, which is really from Tmax until the drug is entirely gone. So the right side of the curve is elimination, absorption, elimination. We've talked about onset of action, duration of action, intensity of action. And so all of these terms, once you understand, you can actually see and understand a lot about a drug by carefully examining its plasma drug concentration time curve. And that was the idea behind this slide. Now, let's move on to another important topic. We're assuming at this point that the drug has been absorbed. With the bioequivalence and bioavailability issues, a drug is eventually released. And as we've talked about in the plasma concentration curve we just went through, the first phase is absorption. So the drug gets absorbed into the plasma. Now, what happens at that point? Once it goes into the plasma, an important consideration to understand is that some of the free drug molecules will bind with certain plasma proteins. For example, albumin is a major protein constituent of plasma and has the ability to bind certain drugs. So in the blood, once the drug has been absorbed and into the plasma, it exists in a equilibrium to some extent between the certain amount of drug that's free versus a certain amount of drug that does become bound to this plasma protein. And the reason that this is important, as you can kind of see on this picture on the right-hand side, is that it's only the free drug molecules that can leave the plasma to produce a pharmacologic effect on whatever tissue that drug works on. If it's bound to the plasma proteins, then it's held captive. It's not free to be able to be released and therefore diffuse into or be absorbed into then whatever biologic tissues that drug needs to work on. Therefore, a drug with a relatively high plasma protein binding rate, that is, most of the drug is bound to plasma proteins, means that there is less free drug, meaning there is less ability to produce a biologic effect. Conversely, a drug with a very low plasma protein binding rate would have a greater effect on being able to leave the plasma to produce its biologic effect. So what this next topic has to do with is determining essentially the relative fraction of the amount of drug in the plasma that's bound to protein versus the amount of drug in the plasma that's not bound to protein. And we talked about why that's important. So let's put some variables into play here. We're going to call CT stands for the concentration total of the drug in the plasma. Whether it's bound or unbound, the entire, regardless of that, the total concentration is going to be abbreviated CT. So the total obviously is made up then of these two fractions. The first fraction we're going to abbreviate as CB, and that represents the plasma concentration of the drug that is bound to plasma protein. And I'll remind you, if it's bound to a plasma protein, then it's not available to produce a biologic effect. Then conversely, the other part to the total would be the unbound plasma concentration, which we're going to abbreviate CU. The unbound obviously is a fraction of the drug which would be available to produce a biologic effect. Therefore, how do we compare or determine this important percentage? Well, we're going to use a variable called alpha. So the fraction alpha is defined as the unbound drug concentration divided by the total drug concentration. Okay? It really is the fraction or the percent of the drug that's unbound. And that's important because, again, it's the unbound portion of the drug or the amount of the drug that's an important indicator of this drug's ability to produce a biologic effect. So again, alpha is equal to Cu, the unbound concentration, divided by Ct, which is the total concentration. And I'll remind you, the total concentration is the combination of both the bound and the unbound. So given that definition, let's do a fairly simple question. It says, what is the alpha value of a drug if 1/3 is bound to protein in the blood? Okay. So to answer this question, let's first set up our equation, because we said that Ct, or the total concentration, is equal to Cb, which is the bound concentration, plus Cu, the unbound concentration. The total is equal to the bound plus unbound. Well, what were we told in the question? We were told that essentially 1/3 of the total is bound to protein. Okay, so 1/3 goes with the CB. All right, and since we're dealing with fractions here, we know that if 1/3 is bound and the only other component is unbound, then clearly the unbound fraction has to be 2/3, because 1/3 plus 2/3 equals 1. So we can set up the equation again using numbers that says 1 times CT, essentially, 1 CT, is equal to 1/3 of the CB plus 2/3 of the CU. Okay, because 1/3 is bound. That means that has to be 2/3 left unbound. And then going down, you can remember that the alpha was equal to the unbound concentration divided by the total. So if we say 2/3 of the concentration is unbound over the total concentration, which would be 1, therefore 2/3 divided by 1 is equal to 2/3. That means our alpha, if we go ahead and divide that into a number, is essentially equal to 2/3 or 0.67. So 67%. Or 2/3 of this drug is essentially unbound. Okay? And so the math on this was just supposed to be illustrative of the important idea, though, for understanding how effective, how much pharmacologic activity a drug may have, isn't just limited to the amount or the dose administered or the dose absorbed, but will also be partially dependent on how much of that dose is actually available to be released from the blood and absorbed into the tissues. Again, the greater the plasma protein binding, the less of that dose that's even available to be able to produce a biologic effect. So another interesting aspect of drug action within the body is the degree of its plasma protein binding. All right, let's move on to our next a very important pharmacokinetic term, and the term is called the volume of distribution. Okay, and it's abbreviated capital V, little d. So if I say VD, don't laugh at me, it means volume of distribution. And it's actually called an apparent volume of distribution because it's a fictitious volume. It's not a real compartment within the body. And it's kind of cool. Once you understand what this value means, it really does explain a lot about the drugs, but it can be frustrating for students because you need to understand it's not a real place. It is an apparent volume of distribution. It is what the drug appears to disperse in. So let's just take a step back and deal with, again, so I said that the volume of distribution, VD, is a theoretical volume, and it's the volume that would be necessary to contain the total amount of administered drug at the same concentration that it's observed in body plasma. It's defined as the distribution of a medication between the plasma and the rest of the body after it's dosed. Remember, for a drug to do anything, it has to leave the blood or the plasma. It has to get into tissues. And there are lots of things. The one we just talked about was plasma protein binding that can influence how well the drug can leave the blood to produce a biologic effect. So what a volume of distribution is that it's this apparent or fictitious volume that represents the degree to which the drug is distributed in body tissues rather than the plasma. So it should make sense that the higher the VD, the volume of distribution, the greater amount of tissue distribution, the greater amount of drug that's at least available to produce a biologic effect. It's even possible to get a volume of distribution greater than that of total volume of body water, which is about 42 liters in humans, because remember, tissues can actively take up and concentrate a drug. Drugs don't just move around the body due to passive diffusion. Tissues will concentrate them. So it can pull enough of that drug that it can actually appear to disperse in a volume that's even greater than total body water, which is 42 liters. Now, not all drugs do that, but it's a possibility. Okay, so what is it about a drug that will contribute to it having a higher VD versus a drug that might have a very low volume of distribution? So, in rough terms, a drug with a high lipid solubility, and those are often non-polar drugs, and drugs with low rates of ionization, and those with low plasma protein binding have higher volumes of distribution. Okay, they're able to leave the blood to go somewhere in the body. We don't know where, but they're not in the plasma anymore. Those have a high volume of distribution. Now compare those to drugs that are more polar or that have a higher degree of ionization in plasma or exhibit a high degree of plasma protein binding. Those are all things that are going to hold the drug into the plasma, limit its ability to leave the plasma and to get into tissues to do any sort of pharmacologic effect. So, with that as enough of an introduction, let's start using the VD, and let's use it in an equation and define it. So now we know what VD, what it means. How do we actually calculate it? So on the formula on the right here, you can see that our volume of distribution, I'll remind you, capital V, little d, volume of distribution is equal to D divided by CP. And D stands for the dose of the drug that we give, divided by the plasma concentration we get from that dose. So to determine a volume of distribution, all you need to do is administer a dose of the drug and then determine its plasma concentration. Because if you take the dose divided by the plasma concentration you got from that dose, you get the volume that drug appears to disperse in. So with that enough of a description, let's actually do a problem. This question says, a patient received an intravenous dose of 10 milligrams of drug. A blood sample was obtained containing 40 micrograms per 100 milliliters. Now, based on that dose and that blood concentration, calculate the apparent volume of distribution for the drug in liters. So we got to be careful with our units here. All right. So let's first define our terms. We said that VD was going to equal dose D divided by CP, which is plasma concentration. So let's first define what our dose was. Our dose was given to us as 10 milligrams. Easy enough. But let's be careful of the units we see that our dose was in milligrams. Because then if we put our CP, our concentration, or plasma, was given to us at 40 micrograms over 100 milliliters. So I can see now that I've got 10 milligram dose, but a plasma concentration in units of micrograms. So the first thing I want to do is simply convert the units on my concentration. I want to go from micrograms per milliliter, and I eventually want, and the question did ask for a volume in liters. So let's convert micrograms to milligrams and milliliters to liters. That way we'll have the right units to go ahead and calculate our volume of distribution. So to make that conversion, I first chose to convert the weight. So let's multiply times 1 milligram over 1,000 micrograms. That way the units of micrograms cancel. Then I'll multiply by the fact that there's 1,000 milliliters in 1 liter. That way my units of milliliter cancels, and my final remaining units would be in milligrams per liter. So if we do that math, going across, you can see the thousands cancel, and essentially you get, if we divide it out, 0.4 is our numeric answer, and our units are in milligrams per liter. So I haven't done anything but simply alter the units of my concentration from micrograms per 100 milliliters to milligrams per liter. And so the equivalent number is 0.4. Now I can use this to set up my volume distribution formula, because VD is equal to dose divided by CP. So my dose was 10 milligrams, and I'll divide that by my 0.4 milligrams per liter. My units of milligrams cancel, and my final value would be in liters. So 10 divided by 0.4 equals 25, and the units are liters. So the volume that this drug appears to disperse in is 25 liters. Okay, and that number by itself may not mean a whole lot other than when you can compare it to other values. Other drugs may have values much smaller. There are some drugs that don't even have a 1 liter volume of distribution. That small of a volume of distribution means very little of the drug is available to produce a biologic effect, whereas a drug with a larger volume like this one, 25 liters, even higher than that, is a drug that definitely goes somewhere else in the body. We don't know where in the body, but having this large volume, 25 liters, means, man, that drug is out there somewhere, because it's not in the plasma. It's not where we put it. It's not where it was initially absorbed into. So it's available to leave the blood or plasma and produce some sort of biologic effect. So that's the whole concept behind the idea of a volume of distribution. All right, let's now move into the latter phase of pharmacokinetics, and it is the term kinetics. You'll notice kinetics in pharmacokinetics means the rate, and so let's actually start talking about some rate constants and calculating some times. This focus will be on the elimination phase. So let's refer back to the plasma protein concentration curve. Remember how there was an absorption phase up until a Tmax. The Tmax was the point at which absorption was equal to elimination. And after the Tmax, there was kind of this continual elimination phase. And hopefully you'll remember, the line wasn't a straight line. It just doesn't go from Tmax straight down to zero in some sort of linear fashion. And that has to do with the way the body eliminates and moves the drug around the body as it eliminates it. And the process, the kinetic terms we're going to define, is the fact that the numeric description of the way to describe its elimination is as a first order elimination. And the term first order is important and describes the plasma concentration curve shown on this slide. So let's just make sure, let's illustrate that. We have a time curve here. So you'll notice on the x-axis on this figure, it starts from 0 and goes to the right out to the value of 10 hours. So there's time in hours along the x-axis. And what we can see on the y-axis is plasma concentration. So if we looked at time 0, I want to make sure you understand, this would be an indication of an IV drug dose, because when you administer a drug into an IV, there is no absorption phase. Pretty much, if you push all of the drug into the blood through an IV injection, then there at time 0, essentially, all of the drug is available to the body. So that's what happened in this example. So you'll notice the total drug concentration at time 0 was around 55. All right, so this is an IV administration with a no absorption phase. So this is essentially Tmax is Cmax is at time 0, because we started with a total highest concentration of around 55. So really, in this kinetic process, we are looking at just the elimination phase. So if you look at the curve, so we've mapped out, and this is a very typical drug. This is the way most drugs look as they're eliminated. That is, there is this rapid, relatively steep slope to the curve for the first amount of time. So if you look at really for the first 2 hours, there is the curve is almost a straight line pointing directly down, because remember, we were looking at the body eliminating the drug, so the drug concentration is going to fall. And it falls relatively rapidly at first. But notice from 2 to 3 to 4 hours, there's a definite bend in the line. It's becoming a curve. It's not a straight line. It seems to be slowing down. And certainly going from 4 out to 8 hours, you'll notice that it continues to slow down, so that instead of actually ever reaching 0 very quickly, it takes longer and longer, because the rate at which the drug concentration is decreasing in the plasma is slowing down. Why is that? It's not linear, okay? It's a first order reaction, which means, and this is the definition, make sure you understand this, it means the rate of the decrease, the rate of elimination is proportional to the drug concentration. So starting at time 0 and going back to the very early phases of elimination, where we had very high drug concentrations to begin with, the rate of elimination was faster. But as we eliminated the drug and the concentrations came down and down and down, so does the rate. There's less drug to drive the elimination. So as the drug concentration decreases, the force or the push to eliminate the drug also decreases. Therefore, the rate of the drug elimination decreases. So throughout this whole process, there's this constant conversion. As drug concentration goes down, then its own rate of elimination goes down, and that's what produces this curved shape. Okay, so remember, at early times, at high concentrations, the rates are faster than at longer periods when the drug has become eliminated and is much lower, but so is its rate of elimination. And this first order process is not unique for pharmacokinetics or in terms of the way the body eliminates it. This is something we'll also describe when you talk about drug degradation. So when you look at formulations of the drugs and their shelf life, how long they stay stable and can be used on the shelf, they break down in a rate that's often described also as a first order reaction. And that's in a separate problem. Here we'll still focus on the way the body eliminates the drugs, and for many of them, it's eliminated by a first order. So all this comes down to is it means the equations we're going to have to use to describe how the body eliminates has to take this first order type of reaction into account. So let's look at some of those numeric descriptions of what we just illustrated in that plasma concentration curve. So what we're going to define is that a first order rate process can be described in general as the derivative of the plasma concentration, that is the change in concentration over the change in time. So the dc dt, okay, the change in concentration as occurs as a change in time is equal to some negative k value times the plasma concentration at the time. So, and again, what K, so understand K is a proportionality constant. It's essentially the defining factor about the actual rate, and it's going to change over time. We give it a negative value, and the reason why there's a negative K is that the concentration is decreasing. So the direction of the curve, the direction of the line is negative. So that's why it's a negative K times the concentration. And we said that the rate at which it degrades is proportional to its concentration. So that's why there is C in the formula. So the change in concentration over time is equal to some negative proportionality constant times its concentration at that time. All right, that's a nice general formula, but not all that useful. Because usually what we want to know is the concentration at a specific time. So how can we go from general into a specific time? So look over on the right. This is the important formula we're going to use here in a little bit. It says that the concentration at any particular time, so CT stands for concentration at some time, is going to be equal to the initial plasma concentration. So C0 is a special concentration. It's the concentration at time 0. So before any elimination has occurred, what was the initial plasma concentration? C0 times E to the negative KT. So we take that negative K proportionality constant times the time that you're interested in. So we take the value of E raised to a negative KT. Okay? So CT is equal to C0 times E raised to a negative KT. That's essentially re-expressing that first order rate process and telling you how to solve for the concentration at a specific time. So what we can do is rearrange that formula. So oftentimes what we need to try to determine could be, for example, the K value. If we need to know the K value before we can predict any of this. So I've rearranged the formula just kind of solving down to how you could more easily get to the K value. So just rearranging it, you could express that same formula to get rid of the natural or the E value. The opposite function of E is natural log. So in the end, you can see I've rearranged the formula and expressed that the natural log of the plasma concentration at time 0 divided by the plasma concentration initial, so CT divided by C0, the natural log of that fraction is what's equal to a negative KT. All right? So that kind of gives you the relationships between all of those. And truly, since we are going to we know the time that we're interested in, and we probably can measure the concentration at that time, really what's left to determine the problem with these formulas is the K value. Truly, different drugs are going to have different proportionality constants. So how, for your drug, do you actually determine the proportionality constant? That's where a little bit of the trick comes in that we'll discuss next. So how do we determine K? And let me just go ahead and say that this K, we were talking about in general, is often abbreviated as KEL, where EL stands for elimination, because as I mentioned before, we are talking about determining the rate of elimination. So this is the rate constant of elimination, which is KEL. And how do we determine it? Well, the answer is it's simply this: we need to be able to calculate the slope of the line of the change in drug concentration over time. Well, that would be easy for a zero order elimination. So don't get confused. I show you this part of this slide here where it says zero order elimination. Had we had a biologic process that proceeded through zero order elimination, it would be easy because when we plot drug concentration against time, you would get a straight line. And a straight line is easy to measure slope because you measure the change in y divided by the change in x. So in that sense, the slope would equal a negative KEL, or a K elimination. So that would have been easy. But our problem here is that if you look at our first order elimination, remember when first order, the change in concentration over the change in time is equal to the minus KEL times concentration times C. So we don't get a straight line, it's a curve. And you can't just take the slope of a curve. So what do we do? How do we obtain a slope from a curve? The answer simply is this. Replot it so you don't get a curve, because you do need a straight line. And for a first order elimination, just plotting drug concentration against time gives us a curve. So we must plot it differently. How? We're going to plot it by not using the drug concentration on the y-axis. We're going to take the natural log of the drug concentration on the y-axis. So if we do that, instead of just plotting concentration, we plot the natural log of the concentration on the y-axis, and then we can still just plot time along the x-axis. Lo and behold, our curve becomes a straight line. So a first-order reaction is linear plotted when you plot the natural log of the concentration against time. Therefore, now we can calculate a slope since our plot, our line, is now linear and not a curve. Okay? So now remember, slope again is just change in y over change in x. And now that we have plotted the log, the natural log of c, the change in y would be the natural log of c2 minus the natural log of c1 divided by the change in x, which is just a change in time. So it would be t2 minus t1. We can use the properties of natural logs, and since the natural log of a minus the natural log of b is equal to the natural log of a divided by b, we can just, hopefully that didn't confuse you, but I'm just saying we can rearrange our last step. It doesn't change anything, but the natural log of c2 divided by c1 is the same as the natural log of c2 minus the natural log of c1. So it's a simpler conversion. So essentially, the slope. We can calculate numerically the slope and essentially say that that slope, which is equal to the negative k, by calculating the natural log of c2 divided by c1 divided by t2 minus t1, and lo and behold, we have a number. And that number can be equal to minus k. And now we can use that to solve various formulas. The reason this determining K elimination is so important is that it is an important value to use in a variety of different formulas in pharmacokinetics, not the least of which is the formula for half-life. And the whole concept of half-life is very important. So let's define it. Half-life, which is often abbreviated as T with a subscript 1/2, so T 1/2, stands for half-life. And half-life is the time it takes for the concentration to decrease to half its initial value. Okay? The reason why this is important is that it turns out for first-order kinetics, the half-life is a constant. So once we know it, it will always be that value. So we can use one set of concentrations to determine half-life, and then we can apply that half-life to any other maybe more interesting concentrations. So to really define this, it says, this is an important idea. It says at a half-life where the concentration has fallen by exactly 1/2. So what does that mean? Is that the CT, the time that we're interested in, compared to its initial value, is the time it takes to fall by exactly 0.5. We want the time where the proportion is 0.5, meaning the concentration has fallen by 50%. So expressing 50% as a fraction would be 0.5. Therefore, CT divided by C0 is 0.5. Okay? Well, now that we know that, let's go back to our initial formula that said we derived that the natural log of CT divided by C0 is equal to the negative KT. Now, I'm substituting T 1/2 for all my T's because I want to use a very specific time. I want to use the time at which the concentration falls by 50%. Okay? And while I don't know what that time is, I know that the ratio of the CT to the C0 at that point is going to be 0.5. So I can set that back into my formula and basically say that means I get the natural log of 0.5, since that's what the proportion is equal to a minus KT. But this KT is the time at which the half-life fell by 50%. The concentration fell by 50%. So now I can continue to solve that because I can take on my calculator and find that the actual natural log of the value 0.5 is equal to a negative 0.693. And that was equal to my negative KT. Now, what I can do to solve for T 1/2, I divide both sides by my negative K, and my negatives will cancel, and my final value, and this is the important formula to remember, is that half-life is defined as T 1/2 is equal to 0.693 divided by K. Now I can use that information and go further with my other formulas. So let's solve some of these questions. Instead of talking about it in just general terms, here's a question. It says, if the half-life of a drug is 4 hours, what percent of the drug administered would remain in the body 15 hours after administration. Okay, so I have half-life and I have a specific time of a concentration I'm interested in. CT is the time after 15 hours. I want to know how much of the drug would remain in the body. Not how much is eliminated, but how much remains. So how can I do this? Well, I can use my half-life. I'll just set this up to begin with. We're going to use the half-life to find K. And then once I know K, I can go back into my initial equation and actually solve for the ratio of CT to C0. Okay, so let's just do that. We said that the value for half-life, or the formula for half-life rather, T1 half is equal to a 0.693 divided by K. Okay, therefore I know my half-life is 4 hours. I can substitute things. So first let me rearrange the formula and say that K then is equal to 0.693 divided by T1 half. That's a simple rearrangement of the formula. Then I can substitute my 4 hours in for my half-life and say that 0.693 divided by 4 hours. Do that math, and I see that my K is equal to a 0.173, and my units are reciprocal hours because it's essentially 1 over hours. So I'm just expressing that units as reciprocal hours, hours to the negative 1. Okay, so all I've done is used my half-life formula that said that half-life is 0.693 divided by K, rearranging that, saying, well, that means K is equal to 0.693 divided by half-life, and since my half-life is 4, I do the math. For this drug, the K elimination is equal to 0.173 reciprocal hours. Now, let's use that number and go back to my original formula that said that the natural log of the ratio of my concentration at time, whatever time I'm interested in, over my initial plasma concentration, C0, is equal to a negative KT. So in this case, now let's get rid of the natural log, because what I'm really wanting for, the question asks for what percent of the drug administered. So it wants to know the fraction of CT to C0. So that's what we're solving for. So let's get rid of the natural log by taking e to the x on both sides. So e to the natural log cancels each other. So on the left, we get just the fraction of CT over C0, and we can say that's equal to the value of e raised to the negative KT. Okay, I can go further now because I have now both my K and my T. We've already solved for the K value, and we said it was 0.173 reciprocal hours. And I know my time of interest, my T, was 15 hours. I want to know what the percent is after 15 hours. And I notice my units are in the same. So I've got 15 hours, and my K is in reciprocal hours. So when I multiply those units will simply cancel. Okay? So truly, my ratio is simply the value. And if we take the 0.173 times 15, that gives me 2.6. And since it's a negative 2.6, so e raised to a negative 2.6 is equal to 0.074. That's the numeric answer. Now, I wanted to express it as a percentage. So percentage is a value per 100. So let's just multiply our final answer by 100. So our final answer would be 7.4, and that would be a percent. So essentially we've said that a drug that has a half-life of 4 hours would have a total percent of its original dose would be 7.4% of that dose would be remaining after 15 hours. So hopefully you can realize how important it is to be able to determine the K elimination, because it is key variable used in almost all of our pharmacokinetic formulas. So to determine K, oftentimes it has to be obtained from a graph. So how do you get the slope and relate it back to the K value of data that's a first order reaction that plots as a curve, as we've talked about? And we've given one example, but there are actually 3 different ways. I just want to kind of quickly sum up 3 different ways that you can plot plasma concentration versus time data and actually change it so that you can get a straight line. And because based off of the way you plotted that value, that straight line can be used to calculate slope that can be related back to K elimination. So the first concept between understanding the 3 different options I show below here is simply this. The formula that we're basing this on that we've talked about already is that the natural log of CT is equal to the natural log of C0, or initial concentration, minus the K elimination times time. So we've talked about that before, and that's great. We'll do one version on that. But you can also rearrange that, and there are reasons to do so, where instead of using the natural log, let's use the log base 10. So without going through that whole derivation, I'll simply restate that formula using log base 10 as that the log base 10 of the CT is equal to the log base 10 of the C0, but now minus KT divided by 2.303. And that 2.303 is the conversion factor to go from natural log to log base 10. So in the end, though, we got to remember for a log base 10 that we are subtracting KT divided by 2.303. So there's a difference there. Now, having said that, there are three different ways that you can take plasma concentration versus time data and plot it in a way to get a straight line. And based off of that, your slopes will be different. So instead of just reading 1, 2, and 3, let me illustrate each of those. And I'll do that using this example. So just so you can understand where the numbers come from, it says, a patient receives an IV bolus injection of 50 milligrams of an experimental drug. The measured plasma concentrations over 18 hours are shown in the table below. And then what we're going to do is plot this data using the three methods described, and we're going to do that in different ways. And I'll just explain that. So it's a good example of, now keep in mind, this was an IV bolus injection, so there was no absorption. Essentially, our time zero, the time at which we squished all of that drug in there, represents the highest plasma concentration that it's going to start with. And it's simply going to go down from there. As the body moves it around and starts to eliminate it, it will decrease, the plasma concentration will decrease from its initial C0 all the way down. But it's going to decrease in a first order reaction. The other thing that's very important to understand about this data here in a minute is that when you squish all this drug in at time zero, you can't measure it at time zero because you can't inject and measure at the same time because the body has to move and has to distribute the drug before you can actually measure it. So you'll notice all of our times, our first plasma concentrations will not be at time zero. They'll be at some other time. In this case, it's at time 1 hour. Our first concentration is at 1 hour. Okay, but remember our C0 was the concentration at time zero, which we can't directly measure. So part of what I'll show you here as well in these graphs is how do you determine C0 when you don't measure it at that time. It takes time before you can do your first measurement. So keep those things in mind. Let's talk about how you can plot this data. Well, the first way you can plot it that's not helpful is just plotting the concentration values on the y-axis against the time in the x-axis. This is our plasma concentration versus time graph that we've talked a lot at. And as we've said before, when you do that, because the drug elimination in the body is a first order reaction, you get a curve. The curve where the slope is higher at first because of the more rapid elimination, but slows down. So this is the plot we cannot use because it is non-linear. We can't determine a slope from it. So what can we do? The first thing we described doing was instead of plotting the actual concentration on the y-axis, let's plot the natural log of CT versus time. Okay, so that shows you what happens when you take the same data and now plot the natural log on the y-axis against time on the x-axis. You get a straight line. And in this case, you could do the change in y over the change in x, and that would equal, that is, the slope on this graph equals negative k. So you calculate the slope, set that equal to minus k. That's an important idea, is what the slope is equal to. In this case, slope is equal to minus k. It brings up this first example, though, where we can say, remember how, well, we also need to know what C0 is, and you'll notice our first data point, though, starts at 1 hour. But when we have a straight line, what we can do is use our ruler and essentially back extrapolate. You'll notice the dashed line is taking a ruler and going from our 1 hour, following the slope and the line, the straight line, back up to where it crosses the y-axis. and where it crosses the y-axis is the concentration at time 0. And even though we didn't measure it, we can extrapolate the value using the linear line and going back from our time that we first measured and using our ruler and doing a straight line back to where it crosses the y-axis. And in this case, therefore, the y-intercept is equal to C0. And you'll see in all of our graphs going forward here, when you plot a straight line, you can back extrapolate to the y-intercept, and that's the value you could set equal to C0. Okay, so this is one way to get a linear line to be able to calculate slope, to be able to calculate k, is to plot the natural log of c against t, and therefore the slope would equal minus k. But it's not the only way. We said we could also plot the log base 10 of ct. Okay, so it's the same concept, but instead of the natural log, we measure the log base 10 of ct, determine that value, plot it against the corresponding time. And you'll notice the graph looks very similar. The numbers are different because the log base 10 is not the same as a natural log. So some of the numbers are different, but the straight line and the way it looks is very similar. So because of that, we can, again, it's a straight linear line. We can determine a slope, the change in y over the change of x. But when we do that, we set that equal to, now this is where it gets a little different, that's equal to a negative k divided by 2.303. So remember, slope on this line would be set equal to negative k over 2.303. So that slope value, you'd have to multiply by 2.303 to get the actual k value. Okay. Also remind here that you can determine a y-intercept by just doing your back extrapolation, and whatever value you get is essentially going to equal now the log base 10 of C0. And the reason why, to be honest with you, you would ever really mess with a log base 10 is not for the reason we just showed, it's for this example. Because instead of using linear graph paper, you can use log paper. And a log paper is simply a paper where it has a linear scale along the x-axis, but the y scale has cycles, and each logarithmic cycle increases by a factor of 10. Okay, so it's not a linear scale on the y-axis, it's a logarithmic base 10 cycle. Okay, so you can see, as I've kind of labeled on this example graph here, the y-axis goes from the not a 0. You never have a 0 concentration on the y-axis on a log scale, but we can set it very low. So it goes from 0.01. The first cycle goes from that low number up to 0.1. But the next cycle increases another tenfold from 0.1 to 1. And then the last cycle on the top goes from 1.0 up to 10. So you'll notice we do not have a linear scale on the y-axis, but therefore we can just plot our concentration. We don't have to take the log base 10 of our concentration. We can just plot the concentration, but we're plotting it on a y-axis that has a logarithmic scale. So it physically puts the lines where you would put your value in different places and actually creates a linear line for you. So that's why many people choose to just plot concentration against time, but to do so on logarithmic paper, which essentially creates a line that shows you the log base 10 of the concentration against time. Therefore, when you calculate the slope of the line you draw, again, it's going to be the slope is equal to the same negative k over 2.303, because remember, the y-axis is scaled as a log base 10 scale. So the slope is still going to equal minus k over 2.303. The advantage to this now, though, is that the y-intercepts will be equal to C0. Since the graph, wherever it crosses the line, has already been essentially plotted as a log, since we're on that logarithmic scale, then C0 is equal to just the y-intercept. And just having done many of these types of calculations and questions, this is often the most easy way to plot drug concentration data. So when you have drug concentration over time, if you plot it on logarithmic paper, then you can just plot the concentration versus time. But remember, the value of the slope is going to equal to minus k divided by 2.303 since it is on log paper. All right, if you're still with me, we have made it to the last slide, and I appreciate you hanging in there with me because this lecture has been very conceptual. It's in describing what pharmacokinetics is, it's impossible to talk about just doing the math without some of the concepts. So let's end, though, this lecture with some basic, straightforward calculations to remind you that, yes, you will learn much more detail about these concepts in actual pharmacokinetic courses, but in the end, we still need some fundamental math skills to apply those formulas and to deal with these issues of drug movement throughout the body. So, simple, straightforward question. It says, in normal subjects, blood makes up about 7% of body weight. Well, there's an interesting fact for you, but what that really means, 7%, this is going to be weight per weight. 7 grams of blood for every 100 grams of body weight. So that's essentially what 7% means. It's going to be a 7% weight per weight. The weight of blood per the total amount of, or per 100 grams of body weight. Because then part 1 says to go ahead and calculate the approximate blood volume in liters for a man weighing 70 kilograms. Okay, so let's start with his weight, 70 kilograms, and we'll need to first convert that back to grams. So let's convert kilograms to grams by multiplying by the fact that there's 1,000 grams for every kilogram, so kilograms cancel. Now I have the weight of this man in grams. I can determine and convert from his body weight to the actual weight of the blood. And because I know it's 7%, 7 grams of blood for every 100 grams of body. So if I set it up that way and multiply, grams of body weight cancel, and I end up in grams of blood. Okay? Now, if we make the assumption that the density of blood is 1, since most of what it's composed of is water, since the density of water is 1, we're going to go ahead and multiply by the fact that there, for every 1 milliliter, it would have a weight of 1 gram, so that the grams of blood cancel. And I've got the volume, but that volume is in milliliters, and the question did want it in liters. So lastly, let's convert milliliters to liters by multiplying by the fact that there's 1 liter on top over every 1,000 milliliters. So milliliters cancel. If I do that math from left to right, I've determined that for a 70 kilogram man, the weight of the blood within him or the volume of the blood within him would be about 4.9 liters. So an average volume of blood for a 70 kilogram man would be 4.9 liters. Why is that important? Well, we're going to use that in the next question. So the next one says, if the drug Zantac reached peak blood levels of about 500 nanograms per milliliter and did so 2 to 3 hours after an oral dose, calculate the total amount of drug in milligrams in the blood of this patient when the peak blood levels are achieved. So it's kind of interesting to see. What we're going to be able to use is the fact that we know that for most men, they have about 4.9 liters of blood. And if we apply that with the fact that after this person took a Zantac dose, his peak levels were 500 nanograms per milliliter, we can determine how much drug was actually in his body at that time. So let's start with his total blood volume, which we said would be 4.9 liters. Convert that back to milliliters by multiplying by 1,000 milliliters over every 1 liter. So liters cancel, and I'm in milliliters. And remember, we were given the blood concentration of Zantac, which was 500 nanograms for every milliliter. So if I multiply by that, then my milliliters cancel, and I'm in nanograms. I know the total amount of drug that was in his blood, but it's in nanograms, and that's not a particularly convenient number. So we need to get to milligrams. So again, you can do that in one step, but that's too much for me. What I can remember is that there are 1,000 nanograms per microgram. So what I'm going to do is multiply by the fact that in every 1 microgram on top, there would be 1,000 nanograms on the bottom, so that nanograms cancel. Now I'm in micrograms. Then I can remember I can go from micrograms to milligrams because I can multiply the fact in every 1 milligram, there's 1,000 micrograms. So now micrograms cancel and I get milligrams. If I do that math all the way from left to right, I could see that there were 2.45 milligrams of Zantac in this man's blood approximately 2 to 3 hours after the dose that they were taken. Anyways, that ends this lecture, and it comes back to hopefully you got something out of this review of pharmacokinetics and see how your math skills are going to be applied in some very important ways in describing how drugs move around the body and how the body moves the drugs around to essentially get them eliminated.